Okay, we're going to be learning about a library class called HashSet. So I've got a HashSet here. We're not going to actually look at the code in the library, but we're going to learn about how it could be implemented. And we're going to learn about two ways. One is chaining and one is open addressing. But first, I want to make sure that you have the idea of a set in general. So a set is going to keep a collection of things and it's not going to store any duplicates. So if I start off here and I just print the size of my set, my size is going to be 0, perhaps not surprising. So now say I want to add something to my set, I could add zebra to my set. And now I should find that my size is 1. Okay, so it just has one element in it. But what if I add zebra 3 times? The important thing about a set is it's not going to keep duplicate, so I should still just have a size of 1. And you can imagine if I remove zebra, then I'm going to get back down to a size of 0. One more method that I want to show you is that I can call contains. So I can check, does it contain the string zebra? And here I need to print that because otherwise I won't see anything. So you can see I've removed it, so my set.contain zebra is false, and then size is 0. So this is important background so that we can learn about two ways of implementing a hash set. One is chaining and the other is open addressing. Okay, we're going to trace through the code that I have here twice. One's for chaining and one's for open addressing. So let's just walk through it. I've got my set, which is a hash set containing strings, and then I'm going to call add a bunch of times, and I'm going to call contains and remove. So I add tiger, I check if it contains tiger, I add panda, I try and add panda again, that won't add a duplicate item. I try and add zebra, I add giraffe, I add bear, lion, camel, I check if it contains camel, and then I'll remove lion. So we'll trace through this twice. And the reason we're tracing through this is to try and understand how methods like add and contains and remove are going to be really similar, but how methods like add actually work. Again, we're not going to look at the source code, but we're going to explain these two methods, chaining and open addressing. Both of those methods are going to rely on some key infrastructure. Whenever we call add, we're going to take the item that we're adding and we're going to call a method named hashcode on it. That'll happen every time. And sometimes we're going to take that item and call .equals on it with another item that's already in the hash set. So when we're thinking about how to implement add or what our choices might be, the key thing is that we need to figure out a reliable way for where we're going to store that so that we can find it later on. And you can imagine just doing this in a list and then you can search through that list to try and find it again. But both of these, chaining and open addressing, are going to implement a strategy where we want to have a reliable way of knowing where we would put it so we can jump right to the spot where we should have put it. And in general, that's going to get us O of 1 or sort of constant time access to be able to add, check if something is in there using contains, or to remove something. Okay, to implement that reliable way of knowing where we would put something, we're going to use that method I mentioned called hashcode. Let's look at that. Okay, so now we're zooming in on that hashcode method. You can see that I set s to tiger, and then I'm going to call s.hashcode, and that's going to give us a number. And no matter how many times I run it, I always get the same number. That is super important. Depending upon what version number of Java you're using, you might get a different number, but it will always be reliable. It'll always be consistent. And we can imagine writing our own hashcode method. We just have to make sure that for the same object, hashcode will always return the same value. So for a string, you can imagine that hashcode could just return the length of the string. We could be certain that for the same object, hashcode would always return the same value. For convenience, let's print out the hashcode of all of the strings that we're going to use in that example main method that we're running. So here I have tiger, panda, zebra, giraffe, bear, lion, and camel. That's what we need. And when I run it, it will give me the hashcode of each of those. And again, that hashcode for each of those strings is always going to be consistent. Okay, now we're ready to trace through the code. Both chaining and open addressing are going to use an underlying data structure of an array. And it's super important to remember that we can access an element in an array in constant time. So if we want the 99th element. We don't have to walk through each of the previous elements. We can jump right to the spot. We can jump right to an index in constant time. That's one of the important properties of arrays that we're going to build on here. Okay, now let's dive into how we do chaining. We're going to represent the underlying array using this diagram here, and I've labeled the indices 0 to 9. Okay, I've got the same main method here. I've got my set is my hash set that's going to hold strings for me. The first thing I'm going to do, so you're going to imagine I am the hash set, and I'm going to try and add tiger. Okay, remember, I need a reliable way to know where I'm going to put it. So first, I'm going to call hashcode on tiger. We can see below that tiger hashcode returns 80, 80, 60, 47. Since I have a 10-element array, I've decided I'm going to use the last digit to decide what index in that array to put it in. So I'm going to put it at index 7. We could have used a different scheme. As long as we're consistent, it will work. Okay, so I go to index 7 and I find that it's empty, so I can add tiger right there. All right, my next line, I'm going to call contains with tiger. I need a reliable way to know where I should put it or look for it in this case. So I'm going to call hashcode on tiger. Hashcode on tiger returns the value shown there. I'm going to use that last digit, or the 7, to figure out what index of the array I should put it at. When I get to index 7, which I can jump right to in constant time, I find that the array element isn't empty. And so what I need to do is I need to compare the thing I'm trying to check for, tiger, to any elements that are at that array index. So I'm going to compare it using the equals method. So I'm going to compare tiger and tiger. I'll find out that they are dot equals, so I'll return true that my set does contain tiger. Next up, I want to add panda. So adding panda, I need a reliable way to know where to put it. So I'm going to call hashcode on panda. I get the value shown there. Again, I'm going to use that last digit, which is a 4. So I'll go and try and put this at index 4. When I look at index 4, I see that it's empty, so I can add panda. Okay, next up, I'm going to try and add panda again. Again, I want a reliable way to know where to put it, so I'm going to call hashcode on panda. Hashcode on panda returns the value shown there. The last digit is what I'll use to figure out which of my array indices to put it at. So I'm going to look at index 4. Index 4 is not empty, and so I'm going to have to compare panda that I'm trying to add to anything that's stored at index 4. So I have to call dot equals with panda and panda. Those are dot equals, so I'm not going to add it, because remember, a set doesn't keep duplicates. Okay, next up, line 10, I'm going to add zebra. I want a reliable way to know where to put it, so to do that, I'm going to call hashcode. Hashcode is going to return the value shown there. I'm going to use that last digit, which is a 0, to figure out what array index to put it at. When I look at index 0, I find that it's empty, and so I can add the string zebra there. Okay, next up, row 11, I want to add the string giraffe. To do that, I need to call hashcode on giraffe. Hashcode on giraffe gives me the value there. And now I'm going to use the last digit, that's the 2, to figure out what array index to put it at. I go to array index 2 and there's nothing else there, and so I'm able to add the string giraffe. And remember, I could have used a different scheme, something other than using the last digit to figure out the array index, but that's what I'm going to use here. And as long as I pick something that's consistent, I'm totally fine. Okay. Next up, I'm adding bear, so I have to call hashcode on bear. That gives me the value shown there. The last digit is an 8, so I should put this at array index 8. I see that index 8 is empty, so I'm able to add bear. Line 13, I want to add lion, so I need to call hashcode on lion. That gives me the hashcode shown there, and its last digit is a 2, so I want to put this at index 2 in my array. When I get to index 2, I find that it's not empty, so I need to compare lion to all of the elements stored at index 2. So I'm going to call dot equals here with lion and giraffe. I find that they are not dot equals, so I'm also going to add lion. Okay, next up, I want to add camel. The first thing I do is I'm going to call hashcode on camel. That gives me the value shown there, and its last digit is a 2. So again, I'm going to try and put this at index 2. When I get to index 2, I find that it's not empty. So I need to compare it to all of the elements that are currently at index 2. So I'm going to call dot equals with camel and giraffe. That's false. Okay, so I'm going to keep going. I'm going to call dot equals with camel and lion. Again, that's false. And so I'm going to add camel to index 2. Line 15, I'm going to check if my set contains camel. Same algorithm, essentially. I need a reliable way to know where I would have put it. So I'm going to call hashcode on camel. Hashcode on camel gives me that value there. The last digit is a 2. So I'm going to look at index 2. I find that index 2 is not empty. And so I need to compare camel to all of the elements that are index 2. So I'm going to call dot equals with camel and giraffe. That's false. I'm going to call dot equals with camel and lion. That's false. And then I'm going to call dot equals with camel and camel. That's true. So I'm going to be able to return that yes, my set contains camel. Last line, I'm going to say I want to remove the element or the string lion. Same algorithm. I need a reliable way to know where I would have put it. So I'm going to call hashcode on lion. Hashcode on lion returns the value shown there. Its last digit is a 2. So I'm going to go to index 2 in my array. I find index 2 is not empty. So I need to compare lion with all the elements at index 2. So I call dot equals with lion and giraffe. That returns false. Next, I call dot equals with lion and lion. That returns true, so I found the lion that I'm trying to remove, and I can remove lion. Okay, so as a reminder, again, here we were looking at chaining, and I hope you can see how we're using both hash code and equals to be able to implement how the hash set actually decides where to put things. And as long as it's consistent about where it is going to put things, it can also use that system to figure out when it's looking for it for a contains or remove where it should be. Okay, for open addressing, I'm going to represent the underlying array with this diagram, and I've labeled the indices 0 to 9. Unlike chaining, in open addressing, each index is only ever going to store one element. That's really important. Open addressing, each index is only ever going to store one element. So to represent that, I'll write the strings inside of the array boxes. So open addressing is going to be different in that we only store one element at each index. And the really important other thing that you'll notice is that we're going to handle it differently when we find an empty array index. And we'll talk through that. Okay, we're going to be working with the same code. And I just added one line. I'm checking for contains camel a second time. Okay, let's run through it. So again, this is a hash set that's holding strings for us. And you're going to imagine that I am the hash set. So I'm executing this. On our first line where we want to add tiger, remember, again, we need a repeatable way to figure out where we would put it. So we're going to call hashcode on tiger. Hashcode on tiger returned that number over there. And we're going to, again, use the last digit because we have 10 array elements. We're going to use the last digit to determine which array index to put it at. So the last digit is a 7. So I'll go to index 7. I'll find that it's empty. And so I'll put tiger at index 7. Okay, my next line to check if my set contains tiger. Again, I need a reliable way to know where to look for it or where I would have put it. So I'm going to call hashcode on tiger. Hashcode on tiger is going to return that number there, 80, 80, 60, 47. I have decided to use the scheme where I use the last digit, so that's 7, to look for it at that index. So I'm going to go to index 7, and I find it's not empty. So what I'm going to do is I'm going to call dot equals with tiger that I'm trying to check for and the tiger that's already at that spot. I find that they are dot equals, so contains returns true. All right, next up, I'm going to add panda. I need a reliable way to know where I would have put it, so I'm going to call hashcode. Hashcode returns the value shown there. That last digit is a 4, so I'm going to look at index 4. I find that index 4 is empty, and so I can add panda there. My next line, I'm going to try and add panda again. Remember, we're working with a set, so we're not going to keep duplicates. So I need a reliable way to know where I would have put it or where I should put it. And so I'm going to call hashcode on panda. And then I decided on the scheme to use the last digit, but I can use anything as long as it's consistent. The hashcode of panda returns that number. I'm going to use that last digit, which is 4. So I'm going to look at index 4. I find that it's not empty. So what I'm going to do is I'm going to compare panda that I'm trying to add with the panda that I already add using dot equals. And those are dot equals. So I don't need to add another copy of it. Okay, next up, I want to add zebra. I need a reliable way to know where to put it, so I'm going to call hashcode. Hashcode returns the number there. I'm going to use the last digit, which is a 0. I look at index 0, and I find there's nothing there, so I'm able to add zebra. And you might have noticed that I'm trying to use colors in a consistent way throughout this Any element with the same last digit in their hash code will have the same color. Okay, I've added zebra. Let's go on to giraffe. So I want to add giraffe, so I need a consistent way to know where I want to put it. So I'm going to call hash code on giraffe. Hash code on giraffe gives me the number there. Its last digit is a 2, so I'm going to look at index 2. I find that index 2 is empty, so I'm able to add giraffe. Okay, next up I want to add bear. So I'll call hash code on bear. I get the value there. The last digit is 8, so I look at index 8. I find it's empty, and so I can add bear. Next up, I want to add lion. I need a reliable way to know where to put it, so I'm going to call hash code. When I call hash code, I get that number there. The last digit is a 2, so I'm going to go to index 2. Okay, but index 2 isn't empty, so I need to call dot equals with the lion that I'm trying to add and the giraffe that I find at index 2. They are not dot equals. I still want to store lion, but I've decided that every array index is only ever going to hold one item. So I need to find an open array index where I can put lion. I can't put it at index 2, so I'm going to try one ahead and try and put it at index 3. I find that index 3 is empty, and so I'm going to put lion there. Okay, next up I'm going to try and add camel. I want a reliable way to figure out where to put it, so I'm going to call hash code. Hash code returns the number there. Again, the last digit is a 2, so I'm going to look at index 2. I find index 2 is not empty, so I compare the camel that I'm trying to add with the giraffe that's in index 2. They are not dot equals, but I still need to find a place to put camel. So I'm going to go from index 2, which is full, and check index 3 to see if it's empty. Index 3 is not empty. But remember, I need to double check that camel's not already in here. So I'm going to compare the camel that I'm trying to add with what I find at index 3, which is lion. Those are not dot equals, but I still haven't found where I can put camel. I tried index 2, now I tried index 3. Next, I'm going to try index 4. I look at index 4, and index 4 is also not empty. So I need to compare the camel that I'm trying to add to what I find at index 4, which is panda. They are not dot equals. So again, I need to keep going. I've tried index 2, I've tried index 3, I've tried index 4, now I need to try index 5. When I get to index 5, I find that it's empty, and I can add camel at index 5. Okay, we'll get to see some of those same steps repeated when we look for camel using contains on the next line. So let's do that. Okay, I want to check if my hash set contains the string camel. I need a reliable way to know where I want to put it. So I'm going to call hash code on camel. Hash code on camel returns the number there. I'm going to use the last digit, which is a 2. So I'll start by looking for it at that array index. I look at index 2 and it is not empty. And so I compare the camel that I'm trying to add to the thing I find at index 2, which is giraffe. They're not dot equals. And so I need to go to the next index, which would be the next place I would try and put it. So now I've checked index 2, I need to check index 3. At index 3, I find it's not empty, so I need to compare the camel that I'm checking for with the thing I find at index 3, which is lion. I use dot equals and I find that they are not dot equals. Now that I've checked index 3, I need to check index 4. I want to see if index 4 contains camel, so I'm going to compare the camel that I'm trying to check for with the panda that I find at index 4. They are not dot equals, so I'm going to go on to index 5. At index 5, I find it's not empty, so I need to compare the camel that I'm trying to check for with the thing I find at index 5, which is camel. Okay, they are dot equals, so I'm able to return that yes, my set contains camel. Okay, next up I want to remove lion. Remove, contains, and add, they all use the same basic algorithm to figure out where I should look for that element. So I'm going to call hash code on lion. Hash code on lion returns the number there. The last digit is a 2. That's the digit I'm going to be using to figure out where to look. So I go to index 2. I find it's not empty. So then I need to compare the lion that I'm trying to remove with giraffe that I find there. They're not dot equals. So I'm going to go to index 3. I find index 3 is not empty. So I'm going to compare the lion that I'm trying to remove with actually the lion that I find at index 3. So I found the thing I want to remove. Here's where I think it gets really interesting. Can you imagine that if I just remove that lion, I would no longer be able to find camel? Because if somebody was looking for camel, they would check index 2, not find it, then get to index 3, find that it's empty, and assume that camel wasn't in there. So I need to do something trickier than just remove lion outright. And what we call this is we're going to put a gravestone in. So I'll represent that as a little RIP. And that's going to help me remember there used to be something here. We can look at how that will work trying to look for camel. Okay, so the next line is my set.contains camel. So I want to look to see if my set has camel in it. I need a repeatable way, so I'm going to call hash code. That's going to give me that number there. I'm going to use the last digit, which is a 2, so I'm going to go to index 2. I find that index 2 is not empty, so I'm going to compare the camel that I'm looking for with the giraffe that I find there. Those are not dot equals, so I'm going to go to the next index, index 3. At index 3, I find it's not empty, but it's an RIP. It's one of those gravestones. So I know both that this is not my item and I need to keep looking. So I'm going to go to index 4. At index 4, I find it's not empty. And so I compare the camel that I'm looking for with the panda that I find at index 4. Those are not dot equals. So I need to go to the next element. That's index 5. And I'm going to compare the camel that I'm looking for with the string camel that I find at index 5. Those are dot equals, so contains can return true. And you can imagine if index 5 had been empty, I would have checked giraffe and the spot with the RIP, that gravestone, and the spot with panda. And so if I got to index 5 and it was empty, I would know that camel wasn't in there. Okay, so with chaining, we could hold multiple things at a single array index. But here we only have a single item at each array index, which means when we have a collision, so two things should be put at the same spot, I need a strategy for finding a new place to put it. Here I just went one index ahead. You could do more complicated things like, oh, instead of doing one index ahead, do it 3 indexes ahead, and then 3 indexes ahead, and then 3 indexes ahead. But that variation isn't super important for us right now. So if I found that the spot I was looking in was full, I would go 1 index ahead and look for it there. Still full, 1 index ahead until I found an empty spot in my array. And to make all that work, it makes a remove a little bit trickier where I can't just remove it. I have to use this gravestone as a placeholder so I can still find things even if they're not at the index where they initially should be, because they might end up a few indices away. Okay, wrapping up with some key things that were true for both chaining and open addressing. They used an underlying array, and we had constant time access to get to an individual index within that array. That constant time access to an array element is really essential to the efficiency of HashSets. The second piece that's really important is we needed a repeatable way to figure out where we were going to put something or where we were going to look for something. And so we relied on this method hashcode. We relied on the fact for hashcode that for the same input, it will always give us the same hashcode. If I call hashcode on Tiger a million times, every time I'm going to get exactly the same value. And because of that element of consistency or repeatability, we can use that number to design our own scheme for how we turn that number into an array index. And that all takes advantage of the fact that we can access an array element in O of 1 time or constant time. I was working with a super small array, so I used the simple algorithm of just using the last digit. And that algorithm of going from the hash code to the actual index I should look in can be much more complicated as long as it's consistent.